Right now, while you are watching this video, a machine built before the internet existed, before home computers existed, before the engineers currently operating it were even born, has just survived something NASA internally nicknamed the Big Bang. It was not a science experiment. It was not a routine adjustment. It was a simultaneous, all-or-nothing reconfiguration of every remaining power system on a 48-year-old spacecraft sitting 13 billion miles away, executed across a communication delay of more than 16 hours each way, with no backup plan, no second chance, and no possibility of a repair mission if anything went wrong. The procedure was so risky that the team at NASA's Jet Propulsion Laboratory spent months running simulations on replica hardware from the 1970s before they even dared to send the first command. And what Voyager 2 measured in the moments after that procedure succeeded, what its still-functioning plasma instrument detected from inside interstellar space after the power system stabilized, is not what anyone expected. It is not a minor correction to existing data. It is something that directly changes how we understand the boundary between our solar system and the galaxy beyond it, something that has implications for the shield protecting life on Earth, and something that sets up a second, even riskier procedure planned for Voyager 1 this month. Stay with me, because by the time this is over, you will understand why the engineers who pulled this off are calling the results unprecedented, and why what happens next could be the final chapter of the most important scientific mission ever launched. I am your name, and this is your channel. Subscribe now if you want more stories like this, because we are just getting started, and what happens in the next few weeks may not happen again in our lifetime. Let's go back to where this actually begins. Because to understand why NASA just gambled everything on a single sequence of radio commands, you need to understand what is happening to the Voyager spacecraft right now in the summer of 2026 that almost nobody outside the mission control room is talking about. Voyager 2 launched on August 20th, 1977. It was given a trajectory that no other spacecraft has ever matched. A grand tour past Jupiter, Saturn, Uranus, and Neptune, using the gravity of each planet to slingshot toward the next. After Neptune, it kept going. For nearly 5 decades, it has traveled outward at roughly 34,000 miles per hour, crossing the Heliopause in November 2018 and becoming only the second human-made object to enter interstellar space, but the power source that keeps it alive is dying. Voyager 2 carries 3 radioisotope thermoelectric generators, containers of plutonium-238 that produce electricity as the material slowly decays. At launch, they generated around 470 watts. Today, they generate roughly 250 watts. They lose about 4 watts every year. And when the output drops below the threshold needed to operate the remaining science instruments, the mission ends permanently. Earlier this year, NASA made a decision that no scientist on the mission wanted to make. The low-energy charged particle instrument, one of the devices that had been operating since 1977, was shut down, not because it failed, because there was no longer enough power to keep it running. That shutdown followed a pattern that has been repeating for years. Of the 10 scientific instruments Voyager 2 carried at launch, only 3 remain active today: the plasma science instrument, the magnetometer, the plasma wave subsystem. Every other window into the spacecraft's environment has been permanently closed, one by one, as the plutonium fades. But here is where the story takes a turn that almost nobody expected. The engineers at JPL did not simply accept the mathematics of decay. They designed a procedure to fight it. They call it the Big Bang, and it is unlike anything NASA has ever attempted on a spacecraft this far from Earth. Here is how the Big Bang actually works. Instead of shutting down instruments one at a time to conserve power incrementally, the procedure involves reconfiguring the entire power distribution system simultaneously, turning off some components, rerouting others, and replacing powered devices with lower power alternatives in a single coordinated operation. The name comes from the all-at-once nature of the change. Not one adjustment at a time, tested and verified before the next. Everything at once. A complete restructuring of how electricity flows through a machine that is older than the programming languages most modern engineers learned in school. The reason for doing it this way is specifically about survival. During any power reconfiguration, there are dangerous transitional moments when the system is neither in its old state nor its new one. Those moments can trigger fault protection systems, automated safeguards built into the spacecraft that will shut down components on their own if they detect power draws exceeding what the generators can supply. The Big Bang is designed to minimize the time spent in those deadly intermediate states by making every change simultaneously, skipping through the transition as fast as possible. If it works, the new configuration recovers enough wasted power to extend the mission by at least a year, possibly more. If it fails, the fault protection systems could cascade, shutting down instruments that cannot be restarted, ending the mission in a single afternoon from a control room in California. The risk was not theoretical, it was real, and that is why the team tested it first on Voyager 2. Voyager 2 is slightly closer to Earth than Voyager 1, slightly better powered, and therefore the safer test subject. The tests were scheduled for May and June of 2026. Every command sent during those tests took more than 16 hours to reach the spacecraft. Every response took another 16 hours to return. A single diagnostic round trip consumed more than a full day. The engineers sending those commands knew that a single error, a single miscalculation, could permanently silence the only spacecraft humanity has ever operated in the southern hemisphere of interstellar space. And then the commands were sent. The spacecraft received them, and against every expectation built on decades of conservative engineering, the Big Bang worked. Voyager 2's power systems stabilized in their new configuration. The fault protection systems remained quiet. The 3 remaining science instruments came back online and resumed their measurements. And the first data that began streaming home after the procedure was complete contained something that should not have been there. For years, the plasma science instrument on Voyager 2 has been measuring the properties of the interstellar medium as the spacecraft moves through it. Density, temperature, flow velocity. Before the Big Bang, those measurements had already established that the interstellar plasma outside our solar system is denser, more structured, and more turbulent than any model predicted. But in the weeks following the power reconfiguration, as the instrument settled back into its routine, it detected a new signal, a sustained, coherent oscillation in the plasma density that had not appeared in any previous dataset. Not a random fluctuation, not a sensor artifact. A rhythmic, repeating pattern in the interstellar plasma stretching across a region of space more than 500 million miles wide. To understand why this matters, you need to understand what scientists thought they knew about the space between stars. For decades, the interstellar medium was described as a quiet, uniform background, a thin, cold, sparse environment where nothing much happens. The persistent plasma emission Voyager 1, detected in 2017, already challenged that idea. Voyager 2's direct plasma measurements at the Heliopause crossing in 2018 challenged it further. But this new oscillation is different. It is not just evidence that interstellar space is turbulent. It is evidence that it is organized, that somewhere in the darkness beyond our solar system, there are large-scale structures in the plasma that create repeating patterns across distances measured in hundreds of millions of miles. Structures that no model built from Earth ever predicted. Structures that we would not even know to look for if we did not have a functioning plasma instrument physically inside that space, sending back real-time data. The researchers analyzing this data are not using words like interesting. They are using words like unprecedented. Because the only way to detect a pattern like this is to have an instrument moving through it continuously over time. And Voyager 2 is the only spacecraft in history that has ever done that with a working plasma detector. Voyager 1 lost its plasma instrument in 1980. Every other spacecraft humanity has built is still inside the heliosphere. Only Voyager 2 is out there, in the actual interstellar medium, with the exact tool needed to measure this. And here is where this stops being abstract and starts being personal. Because the same interstellar environment that is producing these oscillations is the environment pressing against our solar system from the outside. The heliopause, the boundary that protects every planet, every moon, and every living thing from the full force of the galactic cosmic ray flux, is not a static wall. It is a dynamic, breathing membrane, shaped by the pressure of the interstellar medium on one side and the solar wind on the other. If that interstellar medium contains large-scale organized structures, if it has regions of higher density and lower density, of stronger magnetic pressure and weaker magnetic pressure, then the heliopause does not sit still. It flexes, it shifts. It responds to the interstellar weather blowing against it from outside. What Voyager 2 appears to have detected in the weeks after the Big Bang procedure stabilized its power is evidence of that interstellar weather at a scale nobody anticipated, a kind of cosmic current, a structured flow in the plasma between stars that exerts pressure on our solar system's outer boundary in ways that change over time. And because the heliosphere is the shield that deflects the most dangerous forms of cosmic radiation away from the inner solar system, any change in how that shield interacts with the interstellar environment has direct consequences for Earth. Not tomorrow, not next year. But over the geological timescales that govern the evolution of life on this planet, the stability of that shield matters. And we are only now, for the first time in human history, beginning to measure the forces that determine that stability from the inside. But the story does not end with the measurement, because the Big Bang on Voyager 2 was never the main event. It was the test, and the main event is happening right now. If the Big Bang procedure works on Voyager 2, and it has, the same approach will be attempted on Voyager 1 no earlier than July of this year. Voyager 1 is farther away, more than 15 billion miles from Earth. Its power supply is lower. Its communication delay is longer, already approaching 24 hours one way, and its situation is more desperate. In April of this year, NASA shut down the Low-Energy Charged Particle Instrument on Voyager 1, leaving it with only 2 operating science instruments. The Big Bang is the last meaningful engineering option for recovering enough power to do something that seemed impossible just months ago. If the procedure succeeds on Voyager 1, there's a real possibility that the instrument shut down in April could be switched back on. The team is cautious. They are not promising anything, but they are preparing. Think about what that attempt actually looks like from inside the control room. You're sitting at a console in Pasadena, California, looking at a spacecraft that launched when Gerald Ford was president. You're about to send a sequence of commands that will restructure its entire power distribution system in a single moment. Those commands will travel at the speed of light for 22 hours through empty space before they reach the spacecraft. If the spacecraft receives them and executes them correctly, you will not know for another 22 hours. If something goes wrong, if a fault protection trigger cascades, if a single component fails to switch over, you will spend 22 hours waiting for a signal that never comes. And there will be nothing you can do. No repair mission, no manual override, no second spacecraft to send in its place. Just a 48-year-old machine, alone in the dark, running on the last watts of electricity produced by decaying plutonium, carrying the only working instruments humanity has ever placed in interstellar space. The team at JPL is doing this work with the knowledge that they are the last generation who will ever operate these spacecraft. The original engineers have retired. The programming languages used to communicate with Voyagers are obsolete. The institutional knowledge of how these specific machines behave, what commands they tolerate, and what commands they cannot recover from lives in a small group of people at a single facility. When they are gone, this knowledge goes with them. There is no replacement mission on the horizon, no follow-on spacecraft currently funded, designed, or approved that will reach the Heliopause within the next 25 years. When Voyager 1 and Voyager 2 go silent, the only real-time measurements of interstellar space that our civilization has ever obtained will stop. And the questions these spacecraft are raising right now will sit unanswered for decades. Now, come back to what Voyager 2 actually found after the Big Bang, because there is one more layer to this that deserves to sit at the center of the story. The oscillation pattern detected in the interstellar plasma is not just a scientific curiosity. It is a map, a signature of structure in the space between stars that tells us something fundamental about the galaxy we live in. For centuries, astronomers have studied the interstellar medium from the outside, using telescopes and mathematical models to infer what it should be like. They predicted a quiet, uniform void. What Voyager 2 is measuring, day by day, mile by mile, is something closer to a cosmic ocean. It has currents, it has weather, it has structures that stretch across distances so vast that the human mind struggles to hold them. And that ocean is pressing against the bubble that contains our entire solar system with a force and a complexity that none of those models captured. The plasma oscillation that appeared after the Big Bang procedure may be the signature of one of those currents, a flow of interstellar material shaped by magnetic fields and pressure gradients across the galaxy that Voyager 2 is now moving through. If that interpretation holds up under further analysis, it means that the interstellar medium is not just denser than we thought. It is organized at scales we did not imagine. And that organization has implications for how cosmic rays propagate through the galaxy, how star systems form, and how the heliosphere that protects Earth responds to its external environment over millions of years. Here's what I want you to take away from all of this. Right now, in July of 2026, humanity has exactly 2 scientific instruments in interstellar space. Both are 48 years old. Both run on less power than the light bulb in your refrigerator. Both are operated by a team of engineers who communicate with them using technology from an era before personal computers, across delays measured in days, with no margin for error and no possibility of repair. And both are telling us that the universe beyond our solar system is more complex, more dynamic, and more structured than every model built from Earth ever predicted. We have built larger machines. We have built more powerful machines. We have built machines that cost more money and involve more complex engineering. And none of them have told us what these 2 spacecraft are telling us right now. Because none of them had the one thing that matters most. None of them had the time. None of them lasted long enough to get there. Voyager 2 survived the Big Bang. It is still transmitting. It is still measuring the interstellar plasma, still mapping the magnetic field, still sending home data from a place that no other instrument will reach for decades. And in the coming weeks, the same team will attempt the same procedure on Voyager 1, hoping to squeeze 1 more year, maybe 2, out of a mission that was supposed to end in 1981. If it works, we get more data, more answers, more time with the only windows humanity has ever opened into the space between stars. If it fails, we lose one of those windows forever. Bolted to the frame of each spacecraft is a gold-plated copper disc, the Voyager Golden Record. It carries the sound of human laughter, The sound of rain, the sound of ocean waves, music from across human history, and a map made from pulsars showing where Earth sits in the galaxy. Carl Sagan called it a message in a bottle cast into the cosmic ocean. That message will still be traveling when the sun swallows the inner planets. It will still be traveling when every human city has been erased by time. It is the most permanent thing our civilization has ever made. And it is riding on a machine that currently runs on less electricity than the nightlight in your hallway.